the result is that you end up with an olefin CH3, CH2, C, CH3, double bond CH, CH2, CH3. Now you have a skeleton for the 3-methyl hexane. Now all that you need is a reduction of the functional group. After formation of the CC bond, you end up with this one. So if you reduce it, so I will end up with required compound, that is 3-methyl hexane. So let us take up one more addition of this type. So we will take up the example of benzyl cyclohexane. How exactly we build up this carbon skeleton? A benzyl group here, a benzyl cyclohexane. So just as we thought of 3-methyl hexane, you can build up the synthesis of benzyl hexane using the same type of reactions. The first one will start with a Grignard reaction. So Grignard reaction has to make use of a CH2 MgBr here and a CO group, a cyclohexanone. These two will react to form CHOH here, CH2 and a phenyl group. Okay. Now you can very easily see that this compound is a tertiary alcohol. It can undergo dehydrogenation. So with the dehydration with the loss of a water molecule to give rise to cyclohexylidene, and here you have the phenyl group. CH phenyl. Now you can very easily, once you have built up the carbon skeleton, you can do a functional group transformation here and you end up with the 3-methyl hexane. 3-methyl hexane. So the benzyl hexane can be obtained like this. Just by reduction of this double bond, you can end up. So initially you have a carbon-carbon bond forming reaction, then you reduce this functional group. So the organic synthesis involves basically the carbon-carbon bond forming reaction. So just as the other one, Wittig reaction also can be made use of. So here we make use of the same ketone, and a Wittig reagent is CH double bond triphenyl phosphine. So that will be P plus CH minus and benzene, a phenyl group. So it can be prepared from benzyl bromide and triphenyl phosphine. So if you add this one, so there is, just as Wittig reaction gives an olefin which is having a double bond. Now the reduction of the double bond will give you benzyl cyclohexane. Reduction can give you benzyl cyclohexane. Like this. Okay. So these are the very important reactions, and we also have number of such other derivatives. So you can think of examples of how to build up different carbon skeletons, starting from, these will be the exercises for you to do this one. You have an ester CO2 ET and then treating with C3H7 MgBr. So it gives you CH3. Initially you give a ketone CO, CH2, CH2, CH3, and this ketone can go further to form a carbinol, CH2, CH3, and on dehydration this will give an olefin. So okay, one more. So CH2, one, CH2, CH2, CH3. So 1, 2, 3, 4, 5, 6, 7. You end up with the heptane system now. So with having C double bond CH, CH2, CH3, and this is CH2, CH2, CH3. So instead of 3-methyl hexane now, if I reduce this compound, I will end up with 3-methyl, a methyl CH2, a propyl on this side and a propyl on this side. So a carbon skeleton with 7 carbon atoms are available, 1, 2, 3, 4, 5, 6, 7. So that is a 4-methyl heptane can be prepared like this. So we can extend this logic to any system as you like. So a displacement reaction is the one which we normally use it for carbon-carbon bond forming reaction. That is, if I take a cyclohexanone with a bromine atom, okay, this can be allowed to react with the Grignard reagent C3H7 MgBr. We now say that you end up with the CO group wherever the C3H7 is attached to at this point and a CO. So basically you may think as a simple displacement reaction, but this is not a simple displacement reaction. This is an addition of a C3H7 at this center forming a OH, C3H7, and then MgBr, OMgBr becomes OH, and you have a bromine at this point, and the OH group will displace the bromine forming an epoxide. So that is where you can say that you can classify it as a 1,2 addition to carbonyl group, and now the epoxide can open up in the base, in the presence of a base, to form a double bond and enol. You end up with C3H7 double bond OH. That is nothing but the ketone on tautomerism gives a ketone. So we classify the reactions whether they are 1,2 additions or displacement reaction. In this case, if you say that it is simple displacement of C3H7 minus by and Br, that is a little bit wrong. Okay, like that we can have number of such reactions. So we can be used for this one. So some exercises you can think for yourself also, using the 3-methyl hexane, that's the one which we said, and you can take benzyl cyclohexane making use of CH2NO2, and then on this side you will have an aldol condensation, a Michael addition can take place. So CH2 minus can form a CH minus in presence of the base, and that will attack the center. You end up with a ketone. Of course, you will have CHNO2 cyclohexane. So this is an 1,4 addition to a carbonyl group. So now all that we have built up the skeleton for this one, of course. So this should be aromatic. So if I get rid of this nitro group and the CO group, I can end up with benzyl cyclohexane. The carbon skeleton is prepared and you get benzyl cyclohexane. So all that what we need is you have to convert this. So there are many such retrosynthesis can be carried out using various CC bond forming reactions, and this is the importance of a knowledge of various CC bond forming reactions and the conversion of the target to the target molecule is the important aspects that are needed by an organic chemist. Thank you.